In this lecture, we are going to look more deeply into PCA. We're going to talk about what does PCA actually accomplish? Why do we use it? What advantages does it have? In this lecture, you'll learn that PCA actually does quite a lot, more than what you might expect. Okay, so to start this lecture, I'm going to give you a summary of everything that PCA can do, and for the rest of this lecture, I'll explain each topic in more detail. Again, let me remind you that this lecture is the intermediate level lecture, so if you don't have the mathematical tools to understand this, or you don't care, then you can skip ahead to the code lecture. Okay, so the first thing that PCA can accomplish is dimensionality reduction. That is, we might start with 500 stocks, but when we transform them into factors, we end up with only 3 factors. We saw this in the original height and weight example as well. We started with 2 features, height and weight, and we discovered that they are only controlled by one factor, which is size. The second thing that PCA can accomplish is visualization. Hopefully, it's not surprising that your computer screen is 2-dimensional, and the physical world is 3-dimensional. So if you want to plot a 500-dimensional object, humans don't have the capability to comprehend what that even means. This is directly tied to dimensionality reduction as well, which was the first task. So if we reduce our dimensions from 500 to 2, then we can plot these new dimensions and observe our data. Now obviously, we lose some information in the process, but as you'll learn later, we lose the minimum amount of information in some sense. The third task that PCA can accomplish is decorrelation. As you recall, stock returns are correlated. That is, there is redundant information contained in them. PCA removes this redundancy by having all the principal components be uncorrelated. So for example, if one of the principal components refers to size, there won't be another principal component that is also related to size. Redundancy is removed. Finally, the fourth task that PCA can accomplish is denoising. As you recall from our height and weight example, the direction of largest variance represented size. But there was another dimension with very small variance. Our interpretation of directions with very small variance is that it's just noise. So by discarding those dimensions, we are removing noise from the data. Okay, so now let's discuss each of these topics in more detail. The first topic we're going to discuss is dimensionality reduction. In fact, I've already told you pretty much everything you need to know. If we remove dimensions of the data, which are just noise, then equivalently, we are just reducing the dimensionality. If, for example, we start with 500 dimensions and we go down to 5, then what we're saying is that those other 495 dimensions are just noise. The practical question is, how does this work in code? In code, as you know, we're going to call a fit transform function, and we're going to get back a matrix called Z. Previously, I told you that this matrix is of size n by k, which is only partly true. In fact, it's actually n by d, the same size as x, the original data. Of course, this makes sense, given the fact that I told you earlier that PCA is doing rotation. Rotation in and of itself does not remove dimensions, it just changes the directions. The key point is, we choose k ourselves, typically to be a value much less than d. Conveniently, when we get back the Z matrix, it's already organized so that the leftmost columns are the principal components with greatest variation, and the rightmost columns are the principal components with least variation. That is to say, they are sorted. So we can pick the k most important principal components simply by ignoring the rest of the columns of Z on the right of this matrix. So that's why we can think of the Z matrix as being n by k. We're taking the k leftmost columns of Z, and we know that we can do this because each column of Z is sorted by importance. Alternatively, there is an argument you can pass into the constructor of the PCA class called n-components. This is where you can specify k explicitly, but as you'll see, it's usually a good idea to just do the full transformation and analyze the results yourself. Furthermore, even if you choose k smaller than d, the training part of the model still must be done in full. So you don't gain much in the training process by choosing k smaller than d. You'll see why this is in a later lecture. The next topic of this lecture is visualization. Now this is pretty much self-explanatory after the previous topic. By reducing the number of dimensions to 2, you can make a two-dimensional scatter plot of your data. Now you might wonder whether you are losing information in the process of reducing your data dimensionality. The answer is yes. But the important question to ask is, how much are you losing? As per the previous slide, we already know that by choosing the two leftmost components of Z, we have chosen the two principal components with the most information. For PCA, we can think of variance as analogous to information, although technically, there are more rigorous measures for information. We know that PCA sorts each column of Z so that the dimensions with highest variance will come first. Well, it turns out that during the training process for PCA, which you will learn about next, we also get the variance for each of the dimensions in Z. So that tells us exactly how much each principal component contributes to the total variance. For example, we might find that the first principal component contributes 50% to the total variance. The next might contribute only 30%. The rest might contribute only 1%. So that's the idea. And just as a side note, this is often another visualization we like to make when doing PCA. We don't just want to visualize the data itself with a scatter plot. We want to visualize how faithful this representation is relative to the original data. And we can do that by examining how much variance is contained within each principal component. The next topic of this lecture is decorrelation. It's important to remember that uncorrelatedness does not imply independence. So just because your variables are uncorrelated does not mean they are independent. However, being uncorrelated by itself can still be useful. Recall that correlation is just the scaled covariance. So when we say two factors are uncorrelated, that means their correlation is 0. And this also means that their covariance is 0. Recall that the covariance is just the expected value of xi minus mu I times xj minus mu j. This is sort of a generalization of variance. It tells us whether or not variable I and variable j move the same as each other, move the opposite as each other, or are just not related at all. It turns out that the way we form Z, we make it so that each column of Z is uncorrelated. And this is important in terms of dimensionality reduction. For dimensionality reduction, we don't want any redundancy. If we have any redundancy, that means more dimensions can be removed. So by having each dimension be uncorrelated, we can interpret each factor as being a totally different hidden cause behind the stock's return. The final topic of this lecture is denoising. As you recall, one part of the CAPM is the noise term. It says that any variation of a stock's return beyond what is given by the market return is just random noise. But how do we distinguish between a signal and noise? We return to this idea of variance being of central importance. If variance is big enough, we usually consider that to be signal. If the variance is small, we usually consider that to be noise. Intuitively, you can think of a radio which is trying to transmit a sinusoidal wave. The wave that it wants to transmit is a perfect sinusoid, of course, but the receiver will receive a fuzzy version of that sinusoid. That fuzziness is a result of adding random noise at small amplitudes. So you can still see the original sine wave, but there is noise added to it. What PCA does is it separates the large variations from the tiny variations. And by removing the tiny variations, we effectively remove the noise. And again, in a practical sense, this is accomplished by simply ignoring the rightmost part of Z, since Z is ordered in terms of decreasing variance. So instead of keeping the full n by d version of Z, we just take the leftmost part of Z of the shape n by k, where k is much less than d. Okay, and so in that sense, this is equivalent to dimensionality reduction.